Let's first consider the situation when NADH arrives at complex 1. Here, NADH is oxidized, that is, it loses electrons, which is coupled to the reduction of complex 1. Complex 1 accepts the electrons, and as a result, we produce NAD+. When complex 1 accepts electrons, it can also then pump protons from the matrix of the mitochondria through to the inner membrane space. Next, the electrons are accepted by ubiquinone, shown here as Q in blue. This is simply another redox reaction where ubiquinone accepts the electrons and complex 1 loses the electrons. Once ubiquinone accepts the electrons, it shuttles it through that lipid bilayer through to complex 3, bypassing complex 2. Ubiquinone is now oxidized, and this is coupled to the reduction of complex 3. Complex 3 is a transmembrane protein, therefore it is also coupled with the pumping of protons from the matrix of the mitochondria into the inner membrane space. The electrons are then accepted by cytochrome C in a redox reaction, and they are shuttled over to complex 4. Here, complex 4 accepts the electrons from cytochrome C in a redox reaction, and this is coupled with the pumping of protons from the matrix of the mitochondria into the inner membrane space. Now the electrons that came from NADH are approaching the end of the journey, and they're going to be accepted by their terminal electron acceptor, which is oxygen. So oxygen is reduced to form water, and you can see here in the reaction 2 protons are used. Now I'd like us to look at the exact same pathway, but when we start with FADH2. So in the diagram, let's reset everything so we can look at it again. Unlike NADH, FADH2 is oxidized at complex 2, so its electrons are lost to complex 2, which does not pump protons across the inner membrane space. Next, the electrons are shuttled from complex 2 to complex 3 by ubiquinone in a series of redox reactions. As we saw previously, once the electrons are accepted by complex 3 can then pump protons from the matrix of the mitochondria to the inner membrane space. Electrons are then shuttled from complex 3 to complex 4 by cytochrome C in a series of redox reactions. When complex 4 accepts these electrons, it's coupled to the pumping of protons from the matrix of the mitochondria into the inner membrane space. Next, the electrons that originated from FADH2 reach their terminal electron acceptor oxygen in a redox reaction where we produced water with the addition of 2 protons as shown in the reaction. Now let's understand how the proton gradient, or that increase in the proton concentration that we've generated in the inner membrane space, can be used to produce ATP. Here we can see the protein ATP synthase, also known as the F0, F1 ATPase. In this image, we can see the protons entering the F0 component of the protein, which is the proton channel. Protons inside the F0 component cause the shaft of the ATP synthase to rotate. If you have an ADP and an inorganic phosphate, or PI, within the F1 component of the enzyme, the rotation of the shaft then brings these 2 molecules within close proximity of one another, allowing the reaction to take place, forming ATP. The protons then leave the F0 component, and the ATP, newly synthesized, leaves the F1 component. Now let's watch the whole video sped up so you can see how all the components link together.